Let's do an example of a one-mean hypothesis test from start to finish. Here's our setup. A rando on the internet claims that Octobers in Portland are dry and that average rain is only 2 inches. You, a longtime resident of Portland and a licensed meteorologist, are very sure that is too low. You collect data on total rainfall in Portland from 2007 to 2018, which looks like this. The data shows that every year this is the total amount of precipitation in terms of rain that Portland got. Now, right away, you can see that if the average rain is going to be 2 inches, well, some of these years are lower or right around 2 inches, but overall, most of them are more than 2 inches. So you think probably you are right and 2 inches is too low, but let's go through the hypothesis test anyway. So the first thing we might do is write our hypotheses. First, define mu in words. Mu is the mean Portland October rainfall. Your null hypothesis is that mu is equal to 2 inches, the number given in the problem. The alternate hypothesis is mu is greater than 2. You think 2 is too low, which means you think that the actual mean Portland October rainfall is higher than 2 inches. Next, check the conditions. First is randomization, which I'm lumping with independence so I can discuss them both at once. And then I changed my mind, decided to talk about them separately. The sample is random enough since we have 12 total years. It's not totally a random process, at least not our data collection. Is rainfall itself random? Well, it's random enough, and since it's 12 Octobers, we think it's going to be random enough. And for independence, 1 year's total rain should not change the value in any other year. Technically, there is a more specific definition we might use, but this is fine. And I think that is true. Rain kind of comes and goes. It goes away in the rivers and dries up, and so we are probably set. For the 10% condition, we simply say that yes, 12 years is less than 10% of all possible years. For the last condition, the normal or t approximation condition I'm calling it, we do not have n greater than or equal to 30. We only have 12 values here. So since that's not met, we need to see, are these numbers taken from a phenomenon which follows a normal model? And we don't know for sure if total precipitation would be. We kind of think maybe it makes sense because some years would be a little higher, some years would be a little lower, but in general, maybe a lot of years are around the same. But with a sample size of 12, it's hard to tell. One thing we can do is make a histogram of the numbers. It looks something like this. And you can see this is unimodal. It's not quite symmetric, but it's pretty close. This one is kind of standing out as a possible outlier, this 8.31, which is in this one bar, but it's hard to tell. But I think it's close enough that we're covered. Next, we proceed to do the calculations. And because sigma is unknown in this case, we're not given the standard deviation of the rainfall in every year. We're going to have to use a t-model. So we proceed by finding x bar. We just take all of our values that we have here, we average all of these, and we get 3.9383 inches per year. So already that is almost double our hypothesis, but with random variability, we should still do the test to make sure it's statistically significant. Take these same values and calculate the standard deviation using a spreadsheet program or a calculator, whichever you find easier. We get 2.0413. That number is close to 2, but that's just a coincidence because of the numbers I picked. Now we calculate the standard error of x bar is equal to s over the square root of n, which is equal to 2.0413 divided by the square root of 12, which works out to about 0.5893. Now we calculate our test statistic is x bar, 3.9383 minus the 2 from the null hypothesis. Divide that by the standard error of x bar. Be careful, don't divide it by the standard deviation of the x values themselves, always by s over the square root of n, and you will get approximately 3.289. Now go into perhaps GeoGebra, select the t distribution, or student as it's called sometimes, enter 11 degrees of freedom, do the upper tail because this is a greater than, and you get a p-value of 0.0036. And we can assume, since it wasn't given otherwise, that alpha equals 0.05. P-value is less than alpha, means we will reject the null hypothesis. Now let's just put that in the context of the situation. We conclude that the average precipitation in Portland in October is more than 2 inches. And we do a little happy face because we hope we did everything correctly here.